Hi everybody, welcome back. Today we're going to talk about uncertainty in likelihood inference. A scientific statement, as I've mentioned before, is not one that's necessarily correct, but it is always one that comes with an honest expression of the uncertainty of your conclusions. So, since we're going to be using the likelihood theory of inference, we're going to have to figure out how to estimate our uncertainty, and then how to represent it, how to express it, and how to convey it and present it to others. That's what we're going to do today. And so let's get started. We're going to describe three measures of uncertainty, three ways that you can use to do uncertainty. I'm mainly going to focus on the first two. And the first one is going to be the most intuitive. The second one is going to be the most useful. So I can represent them all in this same graph here, every one of them. So the likelihood function is going to be this purple line. The horizontal axis is the hypothetical value of theta in one dimension. We're going back to one dimension because it's the simplest possible case. We'll do multiple dimensions, of course, but just to convey that in this one graph, we have one dimension. So the horizontal axis are the possible values of the parameter of interest. We're going to call that theta. The vertical axis is going to be the likelihood, the value of the likelihood or the log likelihood. The purple line then is the likelihood. Actually, it should be the log likelihood expression. If we look here, the relative heights at different parameter values can be evaluated by something called the likelihood ratio. You may have heard of a likelihood ratio test. That's where this comes from. You probably are familiar with an F-test in regression. A direct generalization of the F-test in regression is a likelihood ratio test. The only difference is an F-test applies to linear regression, and the likelihood ratio test applies very generally across many, many different statistical models. So once we understand this, we'll be able to use it in quite a wide variety of contexts. A second measure of uncertainty, also a reasonable measure, a common measure, are standard errors, and related to that, confidence intervals. And where does that come from? That comes from the curvature of the curve at the maximum. So the likelihood ratio is based upon one point, comparing the height of the curve at one point versus another point. The curvature at the maximum is this curve. So this is an approximation to the curvature right at this maximum point. And the more curved it is at the maximum, the more certain we are, because the height of the curve at the maximum compared to any other points will be a much bigger difference in the likelihood. A third measure, which you may come across, I'm not going to explain in much detail, but just it's intuitive and it's right here, is the slope at a single parameter value. So if you're interested just in this particular value of the parameter theta, then you can go up to the likelihood and you can look at the slope of that. So it's interesting, the slope of that, if it's flat, then you're at the top of the likelihood. If it's really steep, then probably you're farther away from the maximum. And so based just on that one point, you can calculate how uncertain you are, it turns out, and there's something called Rao's score method, or sometimes also called the Lagrange multiplier method. And so that's all I'm going to say about that, but it's another method of calculating uncertainty. And you can see the most important thing is that all three of the main measures of calculating uncertainty can all be expressed in this little graph that I drew here. Okay. So first we're going to talk about uncertainty via the likelihood ratio. Okay, so here's the way we're going to do it. We're going to have two likelihood models, and we're going to compare them. And this is going to enable us to compare them. If you think about it, it's going to be quite frequent that we're going to want to compare two different models to know which one's best, whether one is enough different than the first to really pay attention to it and to perhaps switch to it. So what are the two models? The first is we're going to call an unrestricted model, and we're going to call the value of the log likelihood at that L star. So that's the unrestricted model, which means it's just the model. But we're also going to have a restricted model, or a model that nests within the whole model. So you can think about it as you run a regression with 5 explanatory variables, and then you set one of the coefficients, let's say the 4th explanatory variable, to 0, and then you run the same regression. That's the same thing as just dropping the 4th explanatory variable. That second regression nests within the first, because if the first the first is more general. It allows that coefficient, which you've assumed to be 0 by dropping it out, to be any value. And if it actually is 0, then it is equal to the special case, or the one that nests within it. There's lots of other cases of a model that nests within another model. In even simpler cases, you only have one parameter. So again, there's just one dimension here, and the vertical axis is the likelihood, or the log likelihood. The horizontal axis is the value of theta. An unrestricted estimate could be, you're allowed to use anything. You just find the maximum anywhere on the curve. And the restricted estimate is you're only going to look in this interval. So that's an example of one that nests within the more general case. Okay, so what's the likelihood ratio? It's literally the ratio of the likelihoods of the two models. Okay, so the likelihood of the restricted model is never going to be above the likelihood for the unrestricted model because it's unrestricted. So we're going to take the ratio of the restricted likelihood divided by the unrestricted likelihood. That's always going to be less than or equal to 1. Because the likelihood ratio, the restricted likelihood is never going to be larger. The likelihood ratio then is the ratio of these two probabilities. So that ratio that I have right there is the likelihood ratio. So let's write this down with a little more detail. So the restricted likelihood, the value at the maximum, that's what the star is L of theta 1 given y is proportional to, and then now this is the definition of likelihood, k of y times p of y given theta 1. And then we're going to have the unrestricted value, which is going to be written down in pretty much the same way, but for a different parameter value. And that's going to be L star. Now we're going to take the ratio of one versus the other. So the ratio of L for theta 1 over the L for theta 2 is going to be equal to the two definitions. But the interesting thing about the two definitions is that since they are based on the same data set, we're only changing the model. We're not changing the data set. K of y is the same in both, right? Because k of y is an unknown function of the data with the true value, theta, set at a particular value. Set at the true value, that's the particular value. So we can test the likelihood ratio for two values, like theta 1 and theta 2. Those are the ones we choose to test it for. One's the restricted value, one's the unrestricted value. And then we're going to take the ratio of these two things. You take the ratio of two things, and the two k's cancel out, and we get a risk ratio, the ratio of these two probabilities. And the interesting thing is, you now know one method of expressing the uncertainty of your conclusions. So if the unrestricted maximum likelihood estimate, in this case, is theta 2, and you want to know how much different is that than some other value, let's say theta 1, and we're going to call that the restricted value. You could estimate it, you could just choose it, whatever it is. You can actually create this ratio, and if you look at those two numbers, you can evaluate it. Now, that ratio is always going to be less than 1, but let's suppose it's 0.5. If it's 0.5, then the unrestricted value, the maximum likelihood estimate, has a traditional probability that's twice the restricted value. That's a meaningful number. Okay? If it's 1, then they're the same. If it's close to 1, then they're nearly the same. So you can actually use that. This by itself tends not to be used very often, but you absolutely could use it. It is a direct consequence of the likelihood theory of inference. It completely fits. There's nothing wrong with it. And I quite like it because it's utterly intuitive. There's no we don't even have any concept of repeated samples from a population that doesn't exist or anything like that. We just take the ratio of those two probabilities and you get something meaningful. Okay, so that's one way of going forward. Let's generalize that a little bit and think about it from a statistical perspective. In fact, from a hypothesis testing kind of perspective. So under Neyman-Pearson hypothesis testing, which we can use to interpret the likelihood ratio, we think about this under the null hypothesis, in which there's no difference between the two, but in which the restrictions have no bite. in which basically you're going to get the same answer for the restricted model as the unrestricted model. So the unrestricted model, for example, is any value of theta, you choose the maximum. If that's the maximum right there, and you choose the restricted value is somewhere in there, you're going to get the same value. It doesn't have any bite. So the null hypothesis is there's no bite. The restrictions don't matter. So here's what we do. According to name and Pearson hypothesis testing, we now start thinking about repeated draws of the entire data set from the same data generation process. If you do that, and then you calculate the likelihood ratio, which is L star R over L star, and then you take the log, and then you multiply by -2, you get this thing called R. What is that? Well, that's equal to, just the algebra is, it's equal to 2 times the difference in the log of the likelihood ratios, just another way to think about it. And it turns out, if you think of it in terms of repeated samples, and you say, what's the distribution under the null of no difference between the two models? What's the distribution? Because even under the null where there's no difference, just due to chance, we're going to find some differences, and that's really the question that we're going to go after. How much of our results might just be due to chance? That's the thing that we're really going to pay attention to. And so it turns out that this particular weird function that I gave you, right, I just said -2 times the log of the ratio, that function was chosen because it has a distribution that we know. And that distribution is chi-squared, so it's a chi-squared distribution. So let's think about what the different parts of this thing are. So R is the realized value of the big R. M is the number of restricted parameters. So you can think of it as if you're running a regression, you set 5 of the 10 variables equal to 0. And you would normally do an F test. You can run a likelihood ratio, setting those 5 parameters. Those are 5 restrictions. So M then is your restriction. M is 5 in that case. So here's what it looks like. This is what a chi-square distribution looks like. It's skewed to the right. It's asymmetric. There's a critical value that we would calculate, and just like we did for the simple case of a difference in means test or regression coefficient, we calculate this by choosing a type 1 error rate, in this case alpha equal 0.05 again. And then we run the analysis and we figure out, well, what is R? What's the observed value of R? And if R is to the right of the critical value, then we say, oh, it's just too unlikely to have come from the null hypothesis in which there's no difference between the restricted and unrestricted models. But if it's to the left of the critical value, then we accept the null. That's the way the thing works. Another way to think about it, a more intuitive way from my point of view to think about it, is to stop worrying about the formalities of the name and Pearson hypothesis testing case. And what you do is you just realize that the expected value of R, of this function up here, right, the expected value of this thing, under the null of no difference is M, the number of restrictions. So if the restrictions have no effect, then you would expect that on average you would get M. It wouldn't be the mean of this distribution wouldn't be 0. It would be M. So that's you would find about that value. If the parameters indicate that the restriction really is wrong, and your result then matters, and the null is wrong, then R, the realized value of the big R, is going to be a good deal bigger than the expected results, because it's the expected results under the null. If you do much better, much bigger, then you're going to be okay. And formally, if it's this much bigger, then you can say it's significant at 0.05. Who cares, really? It's just if it's much bigger than M, then there's some real good evidence that something's going on. So this method now, remember on the page before, I showed you how to do it without the statistical interpretation, without the repeated sampling framework. If you add the repeated sampling framework, then you can think in terms of name and Pearson hypothesis testing. You can represent this with significance levels and things like that if you like. If that's helpful for you to convince your audience, you can do that. The disadvantage of likelihood ratio tests is that even though they work well, you may have to test your value of the parameter versus lots of others, because there's no limit to the number of things that we could test. We could test all kinds of different hypotheses. This value of theta versus this value of theta versus this value, etc. So although this is quite useful for some specific cases where you're trying to figure out, is it my model or that other guy's model? That makes sense. But we might want a more general situation. And so we're going to talk about uncertainty via standard errors. So here's how we'll think about this. We'll go back to this little diagram. And instead of plotting the entire likelihood hypersurface, this is when we have lots and lots of parameters, or computing lots and lots of likelihood ratio tests, then what we could do is summarize the entire curvature of the likelihood near the maximum. And for each parameter, we're going to summarize that with one number, or for k parameters, we'll summarize it with a k by k matrix. So here's how we're going to do it. We have to figure out, given that purple line, how to approximate it. So what we're going to do is we're going to come up with a way of approximating the curvature at a point. So that's the goal now. All right. So how are we going to do that? How are we going to measure the curvature of an arbitrary function that could look like anything? How are we going to measure that? Okay. So here's how we're going to do it. We're going to use the normal likelihood, not the stylized normal, but the normal likelihood, which has a variance and it has a mean, to approximate all likelihoods. And there's going to be a reason to do that because of the central limit theorem. One justification, that is as n gets larger, all likelihoods become normal, actually, if they fit certain regularity conditions. So we're going to use the normal as an approximation. It's always an approximation for a finite sample, so I don't know whether our sample's big enough yet, but let's not worry about that for now. Right now, it's our approximation. So we get to do it, of course, when it's normal, because if the likelihood we choose, if the stochastic component we choose when we build the model is normal, then great. If it's not normal, it turns out we can approximate the likelihood, the log likelihood, with a normal log likelihood. That's not the same as saying if you have a logit model with a binary dependent variable, you can use a normal stochastic component. That's totally different. It's just the log likelihood of that, if even the logit model will eventually become something that looks roughly normal. So we'll use this approximation. Okay. Then what we're going to do is reformulate the normal, again, not the stylized normal, likelihood, with this constant assumption again, that mu of I is equal to beta. So I'm reusing that same setup, only I'm generalizing it just a little. And my only generalization is, instead of the stylized normal with a variance 1, now I have sigma squared here. So I'm allowing there to be a sigma squared, which we're going to estimate. So now we're going to estimate beta and sigma squared. So this is the setup. This is the normal distribution for observation I. This formula is the same formula as we had before, except there's a sigma squared in it. Okay. I reparameterize. Remember, that's that keyword. We reparameterize. Here, the reparameterization is exactly the same as when I introduced the likelihood function. I'm going to assume that mu of I is the same for all observations, and it's going to be called beta. And I'm doing this for approximation reasons. I'll show you what the advantage is. Now I'm going to take the log of the likelihood, and for this one observation. Notice I don't have the summation sign in there. Why is that? Well, because I'm doing it just for one observation. Okay. I'm sorry. There is a summation sign in the way that we have it drawn here. So strike that sentence. In any event, the log of the likelihood is now these two pieces. Okay, I've just written it. My point was that every time I do this, I'm going to write it in a slightly different way, which is mathematically still correct, just so you can get a feel for the concept and not be so obsessed with the particular way that we choose to write the notation. So this is the formula. This is the log likelihood. Then I'm going to take the squared term. Remember I said if we take just this piece without the sigma squared, and without this piece, previously this piece went away because there was no sigma squared in it. And the log likelihood was just this without sigma squared. And I said, this thing, if you multiply it out, becomes a quadratic. So I'm going to multiply it out now because it's useful. And you see this is a quadratic in beta, right? It's a constant term as a function of beta times a linear term and times a squared term, okay? So why is that important? Let me show you. So now I'm going to make the whole thing a function of beta. So now I have one, as a function of beta, I have a big constant term here, although it's not entirely constant because there's a sigma squared in there. But just as if you look at this whole thing as a function of beta, you basically have a constant, a linear term, and a squared term. All right, so I'm going to rewrite it as a, which is a constant, plus b, which is a constant times beta, plus c, which is a constant times beta squared. So that is very specifically a quadratic equation. That's important. So the log likelihood of a normal distribution with a constant parameter for the mean is a quadratic expression. That's the thing that every log likelihood function as n gets larger winds up approximating with certain regularity conditions. C, well, the thing in blue there, is the degree of curvature. Because you remember when you run a regression with x, with a constant term x and x squared, the coefficient on the squared term is how much bend there is in the regression, right? That's how much curvature there is, right? That's exactly what it is. So C is the measure of curvature. So that's what we'll use as our measure of how curved the likelihood is at the maximum, right? It's the coefficient on the squared term. But in this case, the squared term, it's the squared term of beta. Okay, so what does this mean? Let's interpret it. So the squared term is equal to, excuse me, the curvature, c, the parameter, is equal to minus n over 2 squared. Let's interpret that because it has a real interesting meaning. There's more curvature, which means there's more certainty when n is large, because n is in the numerator here. Well, that makes utter sense, right? The more data we have, the more certainty we have. Second is, there's more curvature when sigma squared is small, when the stochastic component of the model has relatively little variability. Well, that makes sense, right? We actually know more. If there's no variability in the stochastic component, then we draw one observation, we know everything there is to know, right? So the less variability there is in a stochastic component, the more we know. Okay, so for a normal likelihood, minus n over 2 sigma squared is a summary of the curvature or our uncertainty. And the bigger the negative number, the better. The bigger the negative number, the more information exists in the maximum likelihood estimate. And the bigger the negative number, the larger the likelihood ratio would have to be in comparing the maximum likelihood with any other parameter value, any other one, right? So that's a very useful thing because you don't have to specify which other one. Okay, so that's the standard error for the normal model. Now let's think about the more general case of standard errors for any likelihood model. When the log likelihood is not normal, we'll use the best quadratic approximation to it, right? Because the normal is quadratic, and any likelihood will eventually be quadratic as n gets larger. So we're going to use the best quadratic approximation to whatever it is. Under the normal, it's exact. So what we do is we take the second derivative of the log likelihood with respect to beta twice, right? And we get that term which we're calling the curvature. Okay. The second derivative is it is exactly the coefficient c on the squared term on beta for any model. For the normal, it's exact. For other models, it's approximate. And we're also going to invert the curvature. We're going to literally do 1 over it to provide a statistical interpretation. So here's the statistical interpretation, which you've probably seen before. The variance of theta hat, theta being our estimates, not only one estimate, but there could be a whole vector of estimates, is equal to, now when we invert, if there's one of them, you just take 1 over it. If it's a matrix, you take the inverse, that's the minus 1 over here. We're going to take the negative of the inverse of the matrix of second derivatives evaluated at theta hat. And that is the variance matrix, or the variance covariance matrix, or the covariance matrix, just different phrases to describe the same thing. Okay, it's the variance of that vector of estimates across repeated samples of the data set from the same data generation process. So here's a quiz. How do you interpret, if I gave you the numbers for these things, sigma hat 1. So what's sigma hat 1? You could pause, think about that, and tell me what sigma hat 1, tell yourself, think about what sigma hat 1 is. What is sigma hat 1? Ding. Okay, what is it? It is, for the first parameter, we'll call it theta 1, for the first parameter, we have a function, so the function is our maximum likelihood estimate that produces this vector of parameters given an input data set. So the first parameter is just the first estimate that comes from that. So we have our data set, we apply it to our data set, we get that number. We would then imagine applying it to an infinite number of other data sets drawn from the same data generation process. There's variability in our estimate across those. We only get to see one, but there's variability in our estimate across those. If we actually calculated the standard deviation, because I asked for sigma hat 1, not sigma hat 1 squared, so the standard deviation across those is sigma hat 1. So that's exactly what it is. Okay, how about sigma hat 2, 1? What is that? You want to think about that? Okay, so if there's two parameters, theta 1 hat, theta 2 hat, those are the two parameter estimates. They come from the maximum likelihood function that we're going to apply to the data. Again, across samples, we're going to apply the same function to every sample. Even though we only get to see one, hypothetically we could apply it again and again and again. And instead of calculating the standard deviation for one of them, now we're going to have two of them, and we're going to calculate the covariance, the sample covariance between those two estimates across repeated samples. And if we do that, then we get sigma hat 2, 1. You might also ask what sigma hat 1, 2 is. Well, the matrix is symmetric because the covariance of theta hat 2 and theta hat 1 is the same as the covariance of theta hat 1 with theta hat 2. Okay. This works in general, not only for one parameter, but for k parameters. It works in k-dimensional space without jello, right? It is completely general. So we'll use this again and again. It can be computed analytically, but it can also be computed numerically, which is really great because you don't have to take this matrix, you don't have to take this second derivative matrix. You may have to in some cases, that's fine, but if you can do it numerically and it works and you're going to get an answer that's relatively fast and reasonably accurate, which is often the case, we'll just do that. And you basically push a button and get the answer. And that's fine. I don't mind you doing that, but I utterly object if you don't understand conceptually what it's doing. So I want you to really understand what it means conceptually. And if you don't understand, please ask. We'll work it out with you. It's a very sophisticated, counterintuitive kind of concept. So what we're going to have is an estimate of the quadratic approximation to the log likelihood. That's what this whole thing is, right? So it's a quadratic approximation to the log likelihood. We don't know that, so we have to estimate it. So we estimate it. Okay. Asymptotically, we go one more step. It's an estimate of the exact log likelihood because asymptotically, that is as n goes to infinity, the quadratic approximation becomes accurate. And so that's the exact log likelihood. Okay. All right. So we're going to stop right here. And then our next topic is going to be simulation from log likelihood. So now we've done we've shown conceptually anyway, and for a very specific, simple example, how to estimate maximum likelihood estimates within the likelihood theory of statistical inference. And then we showed how to estimate different measures of uncertainty of those maximum likelihood estimates. We can now do that in hyperdimensional space. So if we had 25 parameters, no problem. We don't have to try to draw a graph with 25 different dimensions. We can calculate the maximum likelihood estimates. We can calculate the uncertainty of each of those 25 parameter estimates. That's really useful because we don't have to do the graph, and it also will give us a sense as to how good those point estimates are in representing the entire likelihood surface. But then we have 25 parameters. What are we supposed to do with those? Well, those we're going to have to deal with by doing simulation and calculating quantity of interest, and that's what's up next. So see you soon.